Using the notes for AP Calculus on the topic of improper integrals. So improper integrals are just definite integrals that have an infinite limit. So in this case, you can see the limit goes from 0 to infinity. So here's the graph of f of x equals 1 over x squared plus 1. Integrand right here, what we're integrating. So let's remember what this definite integral represents graphically is the area under the curve. The difference is going from 0, from right there, but it goes on forever instead of having a specific finite upper limit. So it represents the area under the curve from there, and it keeps on going. So to see some of these definite integrals that are improper will converge on a specific finite value. Others will go to infinity and not converge, do what's called diverge. So you can integrate this, 1 over x squared plus 1. Well, you can try to use substitution, say you equal the denominator, x squared plus 1, but then the derivative is 2x, and there's no x on the numerator to cancel out there, so that won't work. But if you just look at this, you can see, well, that's the derivative of arctangent, which means if you integrate 1 over x squared plus 1, that'll give you back arctangent of x, because the derivative of arctangent is 1 over 1 plus x squared. And then it's evaluated from 0 to infinity. Then you go ahead and substitute the upper limit infinity, so you have the arctangent of infinity minus the arctangent of 0. So let's start with arctangent of 0 and see if we can figure that one out. So remember, arctangent's defined in either the first or fourth quadrant. It goes between negative pi over 2, positive pi over 2 there, and negative pi over 2 there. In this case, we're at arctangent 0, so looking for what angle does tangent equal 0? Well, it's right here at the point 1, 0, because tangent is 0 over 1, which is 0, and that angle happens to be 0 as well. So the arctangent of 0 is just 0. The arctangent of infinity may be a little harder to figure out. So let's first think about what the graph of y equals tangent of x would look like. Remember, the graph of tangent looks like this. Sketch of it. And remember, it's got vertical asymptotes at x equals negative pi over 2. And at x equals pi over 2, because that's where tangent is undefined. So remember, what arctangent does is the inverse of tangent. So if we're trying to graph based on that, graph what arctangent looks like, since it's just defined between negative pi over 2 and pi over 2. Its graph would look like this. Well, remember, with an inverse trig function, it reverses the original one. In other words, the x and y coordinates get reversed. So instead of there being vertical asymptotes at x equals negative pi over 2 and x equals pi over 2, those would turn into horizontal asymptotes of y equals pi over 2 and y equals negative pi over 2. And then the graph of arctangent, if x and y coordinates get switched, instead of the curve going up like this, it's going to go like this. And instead of the curve curving down like this, if you switch x and y, it's going to end up curving like this instead. So that's the graph of arctangent of x. And if you want to find the arctangent of infinity, well, where you look on the graph as far right as you can go, you can see right here, as arctangent approaches infinity, there's a horizontal asymptote. So the graph approaches pi over 2. Then minus 0 gives you pi over 2. So this one, since we got a specific finite answer, this definite integral, this definite improper integral, you'd say converges. All right, let's take a look at the next one. Here's the graph of 1 over x squared. And this time we're integrating from 1 to infinity. So from 1 right here, all the way to infinity. So we're finding all this area here, see if it converges or diverges. So the way to integrate this one, well, first to rewrite it from 1 to infinity, this is the same as x to the negative 2 dx. And then just integrate using the power rule, using x to the negative 1 over negative 1 from 1 to infinity. You can pull out the negative 1 and then rewrite it as just 1 over x from 1 to infinity. And then keep going, you got negative 1, then if you substitute it in infinity, you have 1 over infinity minus substitute in 1 over 1. But 1 over infinity, 1 over some huge number, that's really, really close to 0. Minus 1 over 1 is 1, gives you negative 1 times negative 1. So this area, definite interval equals 1. Again, since we got a specific finite answer that's not infinite, this definite interval also converges to just a 1 for that. Let's take a look at a similar graph, 1 over x. Well, if it's 1 over x, remember that integrates. You can't use the power on this one. This would be x to the negative 1. That would give you x to the 0 over 0, which is undefined. So this one, remember, you have to remember the formula for 1 over x. Integrates to be the natural log absolute value of x. This is the derivative natural log of x gives you 1 over x. And this is evaluated from 1 to infinity. And then if we plug in infinity, well, infinity is already positive, so absolute value won't affect that. Minus 1 is also positive, so the absolute value does not affect that either. So natural log of 1, this is saying e to what exponent gives you 1? 0. Natural log of 1 is 0. Natural log of infinity, again, let's think about the graph of natural log. Well, we already saw the natural log of 1 is 0. Goes to this point right here, so if we were to graph y equals natural log of x, it looks something like this. So if we look at natural log of infinity, if you look at the far right of the graph, and notice this time it keeps getting bigger and bigger forever. Even though it's not very quickly, it still does. There's no horizontal asymptote. So because of that, it does go up to infinity. And since we have an infinite answer there, this one, you'd say diverges. It does not approach a specific finite value. It just keeps getting bigger and bigger. Again, what it represents is the area from 1 to infinity, but this time it diverges. And that brings us to a general rule for improper intervals. If they're in this form, the integral from 1 to x, 1 over x to the p, where p is the exponent there. If that exponent is greater than 1, then the integral converges, like we saw over here when the exponent was 2 on the denominator. However, if the exponent is less than or equal to 1, then the integral diverges, like we saw right here. So here the exponent was equal to 1, anything 1 or less than that, it diverges. And let's take a look at another one. So you don't have to graph these to figure these out. The graph is to hopefully show what it means graphically, is the area under the curve. In order to integrate this one, you'd have to use substitution, and since the negative x squared is up in your exponent, that's what you be the function inside, that's what you'd say u equals to. Remember on definite intervals, this one's going from negative infinity to 1, you also have to convert the lower and upper limits. So if you substitute in 1 for x, you get negative 1 squared gives you negative 1. And if you substitute in negative infinity, it would be negative infinity squared. Well, negative infinity squared is positive infinity squared, and then you have a negative on that, so it gives you negative infinity squared. And then we've got 4x. And now we can write this as e to the u. And then the derivative of u, du dx, equals negative 2x. So then dx will equal du over negative 2x. And then you can see the x's were reduced out. 4 divided by negative 2, you could pull that out as negative 2 on the outside. So the integral would be from negative infinity squared to negative 1. And we'd just be left with e to the u. And now if we integrate e to the u, we get e to the u. divided from negative infinity squared to negative 1, then a negative 2 on the outside. And then go ahead and substitute in negative 1. So you get e to the negative 1 minus, substitute in negative infinity squared, e to the negative infinity squared. And that leaves us with negative 2. And it's easier to simplify this if you rewrite it without the negative exponents. So e to the negative 1 is the same as 1 over e, minus e to the negative infinity squared is the same as 1 over e to the positive infinity squared. So I have a negative 2 on the outside as a constant, 1 over e. Oops, and I just realized I accidentally left off the negative from right here. So there was a negative there. That makes this a positive 2. Negative 4 divided by negative 2. So these are all positive 2s. Sorry about that. And then minus, well, 1 over e to the infinity squared. E to the infinity squared is some huge number. 1 divided by some huge number is really close to 0. So you get 2 times 1 over e gives you 2 over e. So we got a finite answer, and that means this one converges. Let's look at one last one. Let R be the region between the graph of y equals e to the negative 3x and the x-axis for x is greater than or equal to 2. So it says determine the area of R if it's finite. Well, finite is another way of saying it converges. Or state that it's infinite, that's another way of saying it diverges. So let's sketch what this graph would look like here, see what we're finding. So e to the 3x, or e to the x would normally look like this. It still goes to the point 0, 1 like that. Actually, let's move it up here a little so it's easier to see. Goes to the point 0, 1. But that negative 3x makes it a little steeper like that, and the negative flips it across the y-axis. So it actually looks something like this. It's y equals e to the negative 3x. And then it says between that and the x-axis, for our x is greater than or equal to 2. So from right here, so to set up our integral, the integral in this case would start at 2, you can see, and it keeps on going forever all the way to infinity. And then we'd have just e to the negative 3x minus 0, find the area underneath it. And here you can use the shortcut for u substitution, since what you said u equals to would be fairly simple. The derivative of negative 3x is just negative 3. So remember the derivative of what you said u is a constant. You can just integrate like normal. An integral of e to the negative 3x is e to the negative 3x, and just divide by that constant. So in this case, divide by negative 3. Oops. And since we're integrating, we're using the shortcut there. So this part will look different. That's what you get when you integrate it, and now we can put the brackets around it. From 2 to infinity. Then you can pull out the negative 1/3 front. You can even rewrite this instead of e to the negative 3x, that's 1 over e to the 3x. Get rid of the negative exponent, make it easier to substitute in. And then go ahead and substitute in infinity and 2. So we'll do 1 over e to the 3 times infinity minus 1 over e, plug to e to the 6. So 1 over e to the 3 times infinity, that's about 2.7. That's a huge exponent, really big, much larger than 1, so that's basically 0. So you have negative 1/3 times negative 1 over e to the 6 gives you 1 over 3 e to the 6. So since we got a specific answer, that's the area. It's finite, and it converges. And that concludes the notes for AP Calculus on the topic of improper integral.